Hello, everybody. It's a great pleasure for me to be able to talk. So I wanted to thank you all for this occasion. Just to put everybody on the same page, I wanted to give you the content of what I'm going to be talking about. So I will be talking about the Sustainable Development Goals as a framework for what I'm talking about. And then 3 projects that I'll be going into is air pollution and COVID, climate change and agriculture, and soil contamination in the west side of Atlanta. And then I will conclude. But for each of the topics, I will stop. If you have any questions, please feel free to put them in the chat so that we can raise them at those times or at the end. So first, many of you might know about Sustainable Development Goals, SDGs. These are what have been decided in 2015 as the goals for 2030. And I think we consider them to be 17 goals, usually very separated. But what I want to talk about today is how I envision them to be very linked based off of the 16 and 17 goals, peace, justice, and strong institutions, and partnerships for the goals. I think these are the key goals that link the 3 different components of the Sustainable Development Goals. And in order to achieve everything, I think that we need to really have good partnerships globally to enhance the natural systems component, the human systems and social systems component. In this partnership together, we can enhance these ties so that we can solve them much better. So these, there's a question now already. So these SDGs, Sustainable Development Goals, are developed by the United Nations. So these goals are for meeting by 2030. How can we achieve a better future for the whole Earth and for the whole people living on the globe? So moving on now to air pollution and COVID. I got very much interested in air pollution because of what was happening like this, what this figure is showing. When I started in 2005, this was not available. So when I first went to China and asked the people there what they thought about air pollution, because I was seeing the air like this, a lot of Chinese told me, looked at me and said, "What do you mean air pollution? There is no air pollution here." And so I thought that was very interesting, that how we changed our perception of what we think about air pollution. When you go to China now, everybody says air pollution is such a big issue. And I think communicating and raising awareness through this kind of global partnership was really important. And this was done by the photographer in China, taking a picture from the same spot every single day in Beijing for 365 days to showcase how bad Beijing's air quality was. And I think it is very obvious that there are very good blue sky days, but there are many gray sky days that persist. And I was really interested in how can we make this air quality better so that we have more blue sky days everywhere in the world. And so air pollution, as many of you might know, obviously causes a lot of air quality problems. But also it is a very big problem for adverse health impacts. What I'm showing you here is a lung tissue. When you are in the normal condition, only exposed to this type of good air quality, you can see that nothing is wrong. But if you're exposed to a lot of air pollution like this, it gets inflamed and gets very red and causes a lot of pulmonary and cardiovascular problems. So causing problems in your lungs and in your heart. And then also this type of air quality has a lot of impacts on agricultural yields too. So there is an economic impact. In countries like Nepal, you can have the impacts on tourism, which the country depends on. So it's not just about seeing good blue sky days, obviously, but it has health impacts, economic impacts, etc., that we should be worried about. When I say air quality or air pollution, these are the main chemical species that I'm talking about. So that's particulate matter. Many of you might have heard of it as PM2.5 or PM10. So those can be directly emitted or they can be formed in the atmosphere. And they are extremely small. So you can pick one piece of your hair. This is your human hair. That's about 50 to 70 microns. A micron is a millionth of a meter. That might not make much sense, but you can compare to the fine beach sand, that's also about 90 microns. So compared to your one piece of hair, PM10 that is smaller than 10 microns is 5 to 7 times smaller than your hair. PM 2.5 is 4 times even smaller than that PM10. So you cannot see these particles because they are small, but they can scatter the radiation, both solar radiation and the terrestrial radiation, and that's causing the sky to be gray. Another pollutant that I'll be talking about is the tropospheric ozone. Tropospheric ozone is very different from the particles, so they don't get emitted directly, but they form in the atmosphere. So nitrogen oxides, NOx, that you might have heard of coming from cars, and volatile organic compounds, VOCs, they come from various places. Under the sunlight, they form ozone. So that is the bad ozone that's very close to us, close to the surface, and that's very different from the good ozone, the stratospheric ozone that protects us from the ozone layer. So the stratospheric ozone is preventing the ultraviolet radiation from coming to the earth, preventing us from skin cancer. So it's very important that we realize there are 2 different kinds, and what I'm talking about is this bad ozone closer to the surface. I'm a modeler, so what I do is I use this type of data all the time. But what we need to understand if we wanted to make air quality better is where do these emissions come from? And so this is one global emissions data that I work with. And you can see that in Asia, there's a hotspot in China and in India. And obviously there are places in the US, eastern part is emitting much more. And then there is very red in Europe as well. And then you can see in Japan, there are spots as well. But from here, it seems like we know everything about emissions, but that's actually not at all the case. We don't really know where the emissions are coming from. And so this is one of my research areas. What I'm showing you here is for the PM that I've been talking about. We actually don't know where the emissions are coming from and how much. Looking at these figures, I hope you realize that this Edgar inventory is showing much less emissions, fewer emissions compared to this make emissions. This is a national emissions inventory, and REES is the regional emissions inventory created in Japan. So there is such a big difference in terms of the data sets. And this is carbon monoxide that is the precursor for ozone. There is such a diverse range. And this is the VOC, volatile organic compounds I talked about for ozone. And so what is happening is that we don't know where these emissions are coming from. And I have different sources laid out from 2000 to 2008 in this figure. What we don't know is the total emissions where they're coming from, but we also don't know from which sources the emissions are coming from either. Most of the data sets agree that industry emissions are very big, but still there is a pretty large range among different data sets. And then you can see that the power sector emissions have a lot of variation. And then the transport seems pretty low from China. And you can see that the residential sector is pretty large, and that's another set of research that I do in Tibet. And there is a lot of household burning that happen in China as well. But going back to what this means is that when we do not know where the emissions are coming from, we don't know how the air quality is modeled either. So these are 3 different model simulations using the 3 different data sets. This, the top one is showing for particulate matter. Because the emissions data sets we use were very different, when we run a chemical transport model with these emissions data sets, we get very different results. And the same thing is for ozone as well. And you realize that in eastern part of China, this specific data set is showing much lower ozone levels compared to the other one, for example. And you remember that this one has had much higher emissions to begin with. And so the reason why is that the ozone is much more difficult, much more complicated process, and it's not a linear process. And so when, depending on the VOC levels, if you have low VOC emissions, which is showing at this side, this is NOx emissions and this is VOC emissions. And so I mentioned that ozone is based off both NOx and VOCs. And so these are the ozone concentrations, that's the z-axis that I'm showing. If you are in this range with lower VOC emissions, the lower NOx, the higher ozone. And so if you are in this scheme, lowering NOx emissions is a very bad policy decision. And to be able to understand that, you need the partnership as well. And so many of you might have seen this figure, how the air quality and COVID, how COVID lockdown is impacting the air quality. This one is the NO2 density from the NASA satellite data. NO2 is a part of NOx, nitrogen oxides that I've been talking about. It's a very short-lived species, and that's why when you see a lockdown, when you stop emitting, you see the impact right away on the atmosphere. So we did also something very similar, looked at different city levels, and then we see, we compare this year's data that is in square compared to the 5-year mean for prior years. So from 2005 to 2019, compared to this year's 2020 data, weekly data showing from January through about the mid of July. And you can see this year's is much lower for NO2, the short-lived species that I was showing in the NASA satellite data for various cities in Eastern China. For PM2.5, this is a smaller particulate matter. It's also very similar, and you're seeing much lower levels of air pollution this year because of the lockdown. But you see that for ozone, as I mentioned, it's very different. And so in some cities, like for example, for Shanghai, in 1 week, it's much higher this year. And this might be an anomaly, but you see that most of the, what seems to be a decrease is still within the range. For some cities, we are seeing a statistically significantly decreased ozone levels, but in most places, that is not the case. And so for northern cities, especially for Taiyuan, that is a central part of China where I was showing the reduction in one of the data sets. This is exactly the case where you lowered NOx and in the very low VOC regime, you actually saw an increase in ozone. There is a question about why the data sets are so different. The data sets are very different because it is not possible to be observing the emissions from everywhere. And so what happens usually is to create the bottom-up estimates, meaning based off of the energy use and based off of the estimates of how many cars are driving, how much, etc. So there's a lot of guesses that go into that. And so a lot of researchers use, for example, the national statistics to create the estimates. But sometimes the national statistics have issues because the national total actually don't sum up to the provincial total, for example. And so there is a lot of discrepancies in that, the details of the data sets, that when you create an estimate, there is obviously a very big range in the emissions estimates as well. So in conclusion of this first part, I hope you you now realize that there is actually a very large uncertainty in China's emissions estimates, and we need to do a better job understanding that. It's not just in China, obviously, but the magnitude is very large. There's a lot that we should be doing in this area. And model results are strongly influenced by these uncertainties. COVID lockdown, sometimes people say air quality has got very much better after COVID lockdown. That's not necessarily the case when you look at different species. For nitrogen oxide and for PM2.5, we tend to see much better air quality because of the COVID lockdown, but that's not necessarily the case for ozone in China. And we are seeing that in different places like in London as well. So here for Sustainable Development Goals, I think that good health and well-being, sustainable cities goals is very relevant for air quality. This one is industry innovation. This is very needed for air quality, better air quality. And obviously that affects the life on land. So if we can have better partnership to improve these emissions estimates and to reduce these emissions, I think we can get to better air quality. So next one is climate change and agriculture. I've been mentioning a lot about air pollution. And I think we usually think about industry as for PM10 in China, that was the main thing that was showing. But the other source that's not even coming as a major source is agriculture. And I think that it's very important to think about how agriculture actually impacts air quality and climate change. And of course, agriculture is related to food security, etc. That's very important for sustainable development goals. So agriculture emits a lot of methane and other greenhouse gases that I'll be talking about. And then it also emits ammonia. Ammonia is a precursor for PM, particulate matter as well. So that leads to ozone and particulate matter problem because methane is a precursor to ozone as well. And that leads to different health impacts. So I just wanted to show you this figure from the IPCC Intergovernmental Panel on Climate Change. This is showing the radiative forcing by different greenhouse gas emissions. So the radiative forcing is really showing the difference in energy that's coming in and going out. So the more you have, that means that it's warming the atmosphere. And so CO2, carbon dioxide, is obviously the major greenhouse gas. And methane is the second largest greenhouse gas. Nitrous oxide is the third largest by species. Halocarbons include different species, including ozone, chlorofluorocarbons, etc. So what I've been talking about, this ozone also has global warming potential. That's positive. So I'll be talking mainly about these carbon dioxide, methane, and nitrous oxide moving forward. But just an interesting point to point out, this aerosols, particulate matter that we've been calling, they actually have a negative radiative forcing, meaning as a whole, we assume that they have more scattering impact, so cooling the atmosphere. So what happened in China, for example, when we reduce a lot of sulfur dioxide, that leads to reduced particulate matter, and that caused the increase in the regional temperature. Okay, so going back to the agriculture, I was very interested in nitrous oxide. We don't really talk about nitrous oxide very much. I'm not really sure why, but this is different from nitrogen oxides, NOx, that we've been talking about. NOx was a short-lived species. Nitrous oxide is a greenhouse gas and very long-lived. It is completely inert in the troposphere close to the surface. And so it doesn't react at all, but then it goes to the stratosphere and it actually causes destruction of the stratospheric ozone. So it destroys the good ozone, and it's being steadily increasing, just like CO2, carbon dioxide. And so it's been a pretty big concern. So when I tried to figure out where this largest growth was coming from using the model, what I did was I divided the world into these different regions. And then I tried to guesstimate that these emissions are a certain level for different regions and for different sectors. So I divided them into agriculture, industry, ocean, etc. And then what I found was that I used 4 different sets of emissions estimates. But then whenever I used different sets, the meteorological inputs, whichever I used, I got the increasing trend only for Southern Asia agricultural soil. So Southern Asia included a lot of different parts of Asia, including Japan, China, and India. But that was the only source where the nitrous oxide was increasing in the recent years. And the reason I think, and a lot of researchers agree, is that the nitrogen fertilizer use has been increasing very rapidly. So this is what the fertilizer use is in the world. And this is coming from the developed countries. And then you can see that for China, it's been increasing steadily. It's been the #1 fertilizer user for a very long time, since it surpassed the United States in about the 1980. And then India is another one that's increasing very much, and now it's the 2nd largest. Pakistan is actually the 4th, and so that makes sense that in the Southern Asia, what I'm calling Southern Asia, there is a very big increase in the nitrous oxide emissions. And then when we look at which crop uses the fertilizer the most, it's actually maize, so the corn. And so we were curious, is it possible for us to reduce this fertilizer use, because we believe that this fertilizer use is enhancing nitrous oxide emissions. So can we reduce the fertilizer use for corn so that we are not going to get too much nitrous oxide anymore? So then we looked at climate smart agriculture. Is it possible to sustainably increase agricultural productivity and incomes? Is it possible to adapt and build resilience to climate change? And is it possible to reduce greenhouse gas emissions, including nitrous oxide? And we came up with this system that's called living mulch systems. What we do, this is my collaborator, Nick Hill at the University of Georgia. What he came up with is that we plant white clover that is a perennial, meaning that it comes back every year. You plant that in the winter, and then it grows over the spring. And then right before you plant corn, you create a strip like this, and then plant corn in between the white clover. As corn grows, white clover does not compete with corn, and so it starts dying and gives out nitrogen. What's very important is that white clover is a nitrogen fixer. It can fix nitrogen from the atmosphere and provides it to the soil. And that's why we don't have to put any synthetic fertilizer, because we have white clover providing nitrogen throughout. And at the end, it's still not completely dead. And so then it can come back in the next time, the next year round. So we call it living mulch because it's living together with corn. So we compared that living mulch system with 3 other different techniques. So no cover crop, this is the bare soil where you put a lot of fertilizer. This is the most common in the US. And cereal rye is a very common cover crop in Georgia. So they grow cereal rye over the winter, and you kill everything before you plant corn. The good thing about cereal rye is that it can provide a lot of carbon into the soil, but it's not a nitrogen fixer, so it only provides carbon to the soil. For crimson clover, it is also another type of clover, and this is an annual clover. And so it is a nitrogen fixer. It can provide nitrogen and carbon. You're killing it right before planting corn. So we had 4 different systems, and we were interested in, are we able to grow corn with the same type of yield? And are we able to reduce greenhouse gas emissions? And so what we do, we now have a different system, but at this time in 2016 and 2017, what we were doing was we would cap the chamber like this, and then we would be taking the gas measurements from the syringe every 3.5 minutes to see how the gas accumulates. And then after we collect the sample, we would put it into, we would go back to the lab, and then we would put that sample into the mass spectrometry that can figure out how much gas concentrations existed in the sample for carbon dioxide, methane, and nitrous oxide. We also created this what's called acid trap. So this is able to trap ammonia. We can see how much is emitted from the soil, and then we trap it within here with sulfuric acid, and then try to find how much has been emitted for a certain amount of time, usually 2 hours. So what we find is that there is a significant difference in the soil for the 4 different systems. This is living mulch, this is crimson clover, this is Sierra rye, and this is the bare soil. I think you can see that the soil is very different. This has much more labile carbon content, and it can contain water so much better. But what we also found was that CO2 is emitted much more from this living mulch white clover plot. And so obviously we have much more labile carbon, and that's emitting CO2 so much more as well. And that was very clear from both 2016 and 2017. And we looked at nitrous oxide, and unfortunately that was also the same, even though we did not provide any fertilizer to this white clover system, because white clover was providing nitrogen to the soil already. It actually had much higher nitrous oxide flux emissions compared to the traditional right after the fertilizer. So there is a very big increase from the fertilizer plot right after the fertilization, but then it subsides. For the living mulch, we don't see that because we don't have the fertilizer application, but we have pretty good peaks in the season where we don't see that from other plots. And that was quite different in the 2017. We think that the 2017 seems to be more what's happening every year after that, but still we have a very big peak where it does not happen for the other plots. And it's showing that it's quite difficult to reduce greenhouse gas emissions, even if we didn't apply fertilizer. And for ammonia, it's also very difficult. So even though we did not apply fertilizer to the living mulch, we're still seeing much higher ammonia coming out from the living mulch plot as well, compared to the traditional, the bare soil. And so that doesn't seem like this is the solution for improving air quality and climate change. But what is stunning to us is that we actually were able to collect we were actually able to do these experiments in 3 different countries: Rwanda, Georgia in the US, and in China. We've done that in Brazil as well. We haven't put this on the figure yet. But what we find is that for China, the flux, the emissions level goes with this axis on the left-hand side. For Rwanda and the US, the level is with this right-hand side. You can see that the maximum is 2 nanograms per square meter per second for Rwanda and US, compared to more than 400 nanograms per square meter per second in China. There is such a big ammonia coming out of China's agriculture that I think we need to be concerned about and think about what can we do to reduce these emissions. So to conclude, the living mulch system is increasing the labile carbon content in the soil. And we're finding 2 orders of magnitude higher ammonia emissions from China in the cornfields. So it's been a buzzword to say climate smart agriculture. And usually what that considers is how much carbon can we contain in the soil. And that's a very important concept, but we have to remember that it doesn't mean that just having labile carbon, a lot of labile carbon, is going to sequester carbon. It's so much more than that, and we really have to think about the mechanism where we can make this agriculture much more sustainable and climate smart. So for this, in relation to Sustainable Development Goals, we have zero hunger, obviously. It is very important to be able to produce enough crops for the future, and the good health and well-being comes from food that we eat. And then agriculture is linked to a lot of workforce, and that leads to, if we can find this kind of agricultural system that works for the climate and the air pollution, that's going to be a climate action in the life on land. So we need a better partnership again to be able to make this system better. Okay, I have a couple of questions. I would like to answer that. The first question is, why was there a spike on the flux data from the China and Rwanda graph in the US data? Okay, so let me go back to that. Okay, so I didn't really explain very well. So what this is showing is the daily fluxes. What I wanted to highlight is not really the daily variations per se, but you're right that for China, there isn't that much daily variations, even though if you think about it, this is about 250 and then you have 450. So there is a very big range. But there is a day in the US where we had very minimal ammonia emissions compared to close to 2. So it might seem like there is much more. But so the reason why there is a difference in ammonia flux is also because of the temperature of the day as well. How much temperature there is and how much moisture there is. So that varies, that makes it vary over different days. And also the same for China and the US. It might be more dramatic because in this case, we are including all the data that we got from different plots. And so that is contributing to that compared to Rwanda. The next question, why is there so much ammonia in China compared to the US? Are they using so much more fertilizer? Yes, so China is the biggest fertilizer user in the world. And so they have been putting substantial amount of fertilizer over time. And one of the reasons is it was subsidized quite substantially by the government. And so it was better for the farmers to apply rather than not. And often farmers thought that more application meant more yields, which is not the case. So I think it's also important to build a partnership with the farmers to really figure out what's the optimal value to prevent unnecessary emissions from coming out and still get the yields. Okay, so if not more questions, I'll be moving on to the final project that is about soil contamination in the west side of Atlanta. So we usually think of sustainable development goals to be something for the global south, the developing countries, as we used to call them. So those countries that are still developing, which we now call them as global south. But I do think that there are a lot of problems in the US as well. And what I'm showing you here is the food desert in the US. And so the definition of food desert is that sometimes it varies in terms of the radius, but I'm using here from the Department of Agriculture definition that based on where you live, you don't have a car and you don't have a supermarket within a mile of where you live. And so you can see the cutter, the darker the cutter, that's more than 10%. And then you can probably figure out that the Southeast US is having significant food desert problem. So there are some areas where more than 10% of the population living in that area have no access to fresh produce. So in Atlanta, it has also been a pretty significant problem. And so one of the ways to mitigate that problem is to have gardens. And so community gardens have flourished in Atlanta, and now there are more than 300 community and urban gardens across Metro Atlanta. And I hear that because of COVID, there's so many more urban gardens happening right now. And the city of Atlanta also started what's called Aglanta. I'm not sure if many of you know, but this is the digital food hub, and they really try to enhance urban food production. But I think what we need to think about is that there is a lot of problems with the soil in urban areas. And so there are soil contamination issues in the urban soils. And especially we should be concerned about the heavy metals and metalloids like arsenic, cadmium, lead, and chromium. The health impacts of lead, I think, is very scary because it's not very visible, and we don't necessarily understand when you are exposed. And this is very important for kids. Sometimes the kids are having loss of appetite or weight loss. You don't necessarily think that that's coming from the lead exposure, but that could be the case. And I think it is very important to consider how lead can affect the children's IQ scores. So what happens, what I'm showing you here is the brain system. The usual signal sending mechanism in our brain goes like this. I'm not at all a neuroscientist, so that is not my expertise. But in the usual sense, you will be able to send the signals. But what lead does is to block these signaling mechanism, and so there is no way to communicate. And what happens is this affects children's brain in a way that for planning, setting future goals, etc. And so they have troubles potentially in schools and have lower IQ levels. So if you're exposed to lead, I think this type of graph is probably more useful to understand. This is the usual normal distribution of IQ scores in the US children. So 6 million would be gifted and 6 million would be with intellectual disability. What lead would do is to slide the mean to the left. So the mean would go lower compared to what it used to be. And what that means is that we would have many more with intellectual disability because of this lead exposure. The blood lead levels is often used as a way to figure out how much children are exposed or adults. And then of course it varies. If you're really acutely exposed, it could lead to death. But usually what we see is not too high of this level of lead levels, but we are seeing even if you have very small level of exposure, smaller than 5 micrograms per deciliter, you could still have decreased IQ levels. And so what the CDC, Centers for Disease Control, have decided is that there is just no safe level of lead for children. There are various sources of lead exposure. It's not just from one source. Actually, some traditional cosmetics can have lead. And then you might know about the leaded paint. So leaded paint used to be very popular in different parts of the world. And it became banned in the US in 1978. So before that, the leaded paint was very widely used. And so if you are living in a very old homes with leaded paint, that could potentially be a source of exposure. And of course, many of you might have heard about the Flint. Water pipes is a potential exposure as well. And leaded gasoline used to be very widely available. And in the US, it was banned in 1996. But there are still some places in the world where leaded gasoline is still being used, creating a source of exposure. But I want you to pay attention to this number 15, which is the contaminated soil. So soil can be contaminated from various reasons. And if you grow food in there, the children can be playing in the ground and then can be eating unintentionally or intentionally and then being exposed. And sometimes the food grown in the contaminated soil can also cause exposure by eating them. And so as I mentioned, there is no known safe level of lead for children, but there are several standards that are being placed to reduce this exposure. For soil, this is 400 parts per million. That is decided by the US EPA. And there is different standard for drinking water, for airborne content, and for the blood lead levels. The CDC, Centers for Disease Control, have decided 5 micrograms per deciliter as the reference value. So we were very interested in what's happening in Atlanta. Is there lead exposure in Atlanta where we are? So what I'm showing you here at the background color is the median household income. So you can see that in the southeast of Atlanta, the median household income is much lower than the other parts of Atlanta. And then the bubbles are showing, the size of the bubble is showing the proportion of children under 6 that are screened for blood lead levels. And what was stunning to us was that only about 20% of children are actually being screened. And then in this zip code, that is the downtown zip code 30303, we found that the proportion of children that were being screened and had higher than 5 micrograms per deciliter, the reference values, was 13%. So 13% of kids that were screened had higher level of lead in their blood than the reference value. And if you remember, even lower than reference value, there is no safe level of lead. So this was very concerning to us. What is leading to this type of exposure? And so we decided to focus on this historic West Side area to figure out if soil could be the reason. And we wanted to especially target, because the city of Atlanta was trying to push this to urban agriculture. And so we went to first get the soil samples from background sites outside of Atlanta to see, to compare with the soil levels in Atlanta. And so these were 3 background sites, and then we got samples from 11 residential sites in the historic West Side area, and then 5 agricultural sites within the historic West Side areas. There are so many community and house gardens in that West Side area, and we were also concerned what would happen. So there is a 400 ppm EPA level that I mentioned. And then 3 residential areas turned out to be higher than the EPA screening level. And what is interesting to us is that 75 ppm is actually considered as the safe level for gardening by the University of Georgia Extension. So this is kind of considered as a state level data, and state level standard almost was always lower than what we found, especially for the residential sites. Even for agricultural sites, 2 of them were higher than the 75 ppm. And that made us very concerned. And we also went to analyze for various other heavy metals and metalloids. And so lead, for every sample that we analyzed, the 38 samples that had pretty high levels that we thought had high levels, all had higher than 400 ppm, the reference value. And the zinc was always higher than the state level, this 100 ppm. EPA level is so much higher, so nothing was higher than this, but we were concerned that it was always higher than the state level. These orange ones, some of the samples were higher than the state level data. And what we found when looking at what might be the sources, we found this. This is slag, that is the industrial waste separated from metals during smelting. We think that this might have come mainly from lead smelting, but this had significantly high lead levels. So the soil underneath these slag had about 1,300 ppm of lead. And then these slag themselves had about 1,250. And so we contacted the Environmental Protection Agency, and this has led to the West Side investigation. So this is now the Superfund site. And then they initially started with very small lot in where we found the slag. They have expanded it to 360 lots. And then now they have expanded it to 1,100 lots. And it's unclear how bigger it's going to be, but I think it is very important that we get aware of this problem, and this could happen anywhere, and be mindful of the gardening that is happening right now. We were very concerned about what is actually taken up by the kids. And so we did some experiments to figure out how the soil can actually be taken up by the children. And we found that about 7% of the lead in the soil can be taken up by eating the soil. And cadmium had nearly 60% being taken up by the body. And so considering that some of the samples were high, we thought that this was a concern. So I want to mention that we're trying to see if we can do phytoremediation, meaning using plants to take up the soil lead. Obviously, it's great to, if EPA finds, if you are in that boundary and if EPA finds higher than 400 ppm, then they would excavate the soil. But obviously there are houses outside of that boundary that we already found to be higher than 400 ppm. Rather than waiting, can we do something? This is planting sunflowers to see if we can reduce them. And we are seeing about 20 ppm reduction when it was about 100 or so at the beginning. Okay, so we also did some greenhouse experiment, and then some of them are able to take up quite significantly. But that turns out to be cows and cabbage that what we can eat. And so they turn out that if you grow them and if you eat those vegetables, then you are actually going to increase your intake by eating those. So that is not a good idea either. And so I just wanted to conclude that there's no known safe level of lead. And considering that lead exposure is preventable, we should be doing something about it. We should increase the number of people screened, and we should we should make sure that the soils are safe and healthy, especially for kids. Phytoremediation might be an effective strategy. And I think this is extremely important for sustainable development goals. And it's not just for the US, but it's for everywhere. I hear that there are so many heavy metal issues all over the world that we are not really dealing with. I wanted to also talk about what we are doing. So if you are interested in taking part in screening your soil, we will be happy to analyze that for you. This is going on until mid-November to raise awareness. And we are also doing movie screening, etc., to have more discussion with the public and having a better partnership with the different parts of, not just within the academia, but with different parts of the different stakeholders. So this was the summary. And I want to thank my students who do a lot of work. And these are all my students that I talked about. And these are the collaborators and funding. Without them, I couldn't have done this work. There's a question that I see here. Are there historical maps of the area in which you found the slag? Can slag producers be identified? This is a great question. That's what we've been trying to do as well, actually, doing the archival data to see who might have dumped the slag, because this was intentionally dumped during the times when it was considered stable. So it was not violating any regulation, but the EPA is trying to catch the people that might have done it. And then we are working with historians if that is possible. We've tried to do that through satellite data, and it was much more difficult than we intended. But yeah, if you have any good thoughts, I would love to hear. Okay, I think I answered all the questions. Oh, is there another one? Yes, there's another one. What happens if you uncover buried lead products? Does it emit more? Oh, that's a great question. So if you uncover, what you really want to make sure is that you don't touch them. You don't, if you touch them and you eat them, that's how you get exposed. I think the air exposure is much less. So if you find it, you want to make sure that that's contained so that you are able to dispose of it properly. You can contact the Environmental Protection Agency to have them do that. I think that's probably the best way. But we can also, if you live close, we can also go test if you are interested. Thank you so much.